advantages of working with an exponential model is that there is unbounded growth or decay, meaning that in any situation where y changes proportionally to the size of y, we have exponential growth or decay. If k is bigger than 0, we're talking growth. If k is less than 0, we're talking decay. But that growth is constant growth, and the growth accelerates because as y gets bigger, then k times y will get bigger. And so what we end up with is a function that just continues to go on towards infinity. So we would write, in terms of calculus, we'd say that as t approaches infinity, y goes to infinity. In population modeling, this is not valid at all because we fail to consider what happens as populations get too large. In fact, there's something called a carrying capacity, which implies that every environment can only hold a certain number of that species before food runs short, competition increases, maybe even predators run amok. And so we do want to take that into account. So if you look at this model here, which is called the logistic change model, the exponential piece is still here, but then it's being multiplied by this second factor, which actually has some controlling effect on how big this output will be. You see there's a subtraction in here, and anytime there's a subtraction, there's a chance that this whole factor could be close to 0 or even potentially negative. So we would expect that as we get closer to our carrying capacity, we'd probably have a population that starts to sort of, instead of growing exponentially, starts to kind of level back out. And if we exceed our population carrying capacity, then we would expect the population size to drop until we get closer to that carrying capacity. So we'll investigate a model here. Suppose we have a growth rate of 3% and a carrying capacity of 30 million. Okay, so our growth factor is still the value of k. In this case, it's a positive 0.03 since we're talking about growth. Very rarely are you using this model if you have a decay, but I suppose that's possible as well. And now we would have 1 minus y over 30. So we'll just keep everything in mind being in millions. Okay, so what happens here as y approaches 30? Well, we can begin by investigating this in a tabular form, and we can just look at a couple of values of y as we get closer to 30. So if y was 20, we'd have 0.03 of 20 times 1 minus 2/3 in this case. We'd have 20 over 30. And that would come out to, let's see, 0.03 times 20 times 1/3. We get 0.2. So 0.2 million per year. And now notice that if we get to 25, 0.03 times 25 times 1 minus 25 over 30, 0.03 times 25 times, this will be 5/30ths, get 0.125. 0.125. So notice that the rate is getting smaller. In fact, when we get to 29, then we're multiplying by 1 minus 29/30ths, which is just 1/30th. And so what that second factor is doing, here we get 0.029. What this factor is doing is that if we look at 1 minus y over 30, as y approaches 30, this thing approaches 0. Now, if you do it from the other side, so this is from the left, if you will. If we approached it from the other side, if we say looked at 31, well, now we're beyond our carrying capacity, and so if I did 31. Here I'd insert a 31, but here I'd have 1 minus 31 over 30, and 30 over 30 minus 31 over 30 is negative 1/30th, and so now I actually get a value of negative 0.031. So actually what we're encountering here is if our carrying capacity is 30, as we get closer to the value of 30, notice our slopes go from, I'll just kind of simulate, this is population size, and now I'm looking at, oh, I'm sorry, not population size, but time. And here is y. And what I would see is kind of a sharper slope, a less sharp slope, a slope that continuously gets kind of close to zero. And so this starts to level out. Now, as far as what this looks like down here, depending on where you start, it'll look a little more S-shaped, because at first this 0.03y will be really supported by the 1 minus y over 30. Remember, this will always be, at least as we're approaching 30, this will be between 0 and 1. It'll be closer to 1 when y is really small, meaning that this factor will pretty much almost be nullified. And so we'll get kind of that exponential growth for a little bit at the turning point where the rate actually starts to slow down and starts to look a lot more like this. So at y equals 30, we actually have equilibrium, you'll notice, because if you insert 30 for y, you get 1 minus 30 over 30, which is 0. And actually up here, if you started up high, what we'd notice is that these rates start to decay back down to y equals 30, regardless of where you start. If you started way up here, it might just take a little bit longer, but we would eventually get that. So there is still this exponential shape from above. From below, you start off exponential, typically, as long as you're really close to 0. And then there's a kind of a turning point here where we go from concave up to concave down. And that's a nice feature of this model. So if I were to actually solve this model, dy dt equals 0.03y times 1 minus y over 30, we would still have to treat this whole thing as a function of y multiplied by 1. Okay, this only contains y, so if I divide this whole thing over here, 0.03y times 1 minus y over 30. If you were doing this using calculus techniques, this integral would require a partial fraction decomposition to split up the y and the 1 minus y over 30. And what we would end up with is actually this difference of logs. If you did this by hand, you may end up writing this as 1 minus y over 30. Using technology, depending on what you use, this integral may look a little bit different. And they're going to be equivalent forms. There are just some properties of logs that you could implement to make one of the logs look like another log, but that's not incredibly important here. So this is what we get, and we get t plus c over on the right-hand side. And so now the question is, well, what do we do with this? Because we want to isolate y, but I have a log in both of these terms. So we'd have to use a property of logs. And you may remember this one at some point from working with logarithms, but it is the case that if you have the log of a over b, that is equal to the log of a minus the log of b. And vice versa. So if you have the log of something minus the log of something else, you could write it as the log of their ratio. But before I do that, I'd actually have to pull out this 33.33 because that doesn't account for any coefficients here. And then I'd have ln y minus ln 30 over y, which I could write as ln of y over 30 minus y. I guess I don't really even need the parentheses there, but I'll leave them. Equals t plus c. And now I can divide my 33.33 over and exponentiate both sides. Now when I divide it over here, I'll just leave it as 1 over 33.33t. If you divide an arbitrary constant by a constant, it absorbs that arbitrary constant, or absorbs that constant into the arbitrary constant. And so we could leave it like this. Now we would exponentiate and go about our business. We get k e to the 1 over 33.33t. And on this side, we would get our y over 30 minus y. Now in this case, you do have to multiply out a little bit. I'll leave it here, but what I wanted you to really see is that, notice that, oops, I put the t in the wrong place here. So I will fix that. 1 over 33.33 times t. And so notice that we still do get an exponential function, which is actually 1 over 33.33 is actually the, this is actually 0.03. And that is still coming from our exponential piece. But now when we distribute this all out and isolate y, we're actually going to get a ratio of exponential functions, which is what's going to cause this leveling out to occur. So this is the logistic model used a lot in modeling populations, and is just in general a good thing to think about as far as how do you build a model where you limit something. And a lot of times the answer is, well, you can multiply by an appropriate thing that as you get closer to some value, that factor starts to zero out, which causes your, well, it's a rate of change, so it's causing your slope to become closer to zero as well.